So I think I'll go past that one. I don't mean to talk through this, but I'm just going to show very briefly some of the ways that people have been working in this area recently. So one idea, so a question that comes out of this comparison would be, okay, if we can explore these models, can we find a way to correct the record? In other words, to do what Raup wanted us to do in 1972. And two approaches are here. One is what John Alroy does, associated with the paleobiology database. He carries out procedures of sampling standardization, which I think are generally quite reasonable. And this is based on standard statistical techniques like rarefaction, which ecologists often use, ways of trying to equalize the sampling regime. You have a sample of 5 specimens and a sample of 500 specimens. How do you compare? And rarefaction is one of those techniques that you can use to subsample from the 500 5 and give you a kind of comparable number for comparison. So there's certainly possibilities in there, although I don't think the way it's being done at the moment necessarily does what is claimed. And the other approach is from Andrew Smith, who has tried to find ways to use the rock record to provide factors for modeling the fossil record on an assumption that the amount of rock record is equal through time. So he's trying to take account of the rise and fall in the amount of rock available. Of course, this is based on an assumption of the bias model, so it excludes the common cause a priori. So that's a problem, I would say. But in any case, he works through and takes residuals that he plots rock record against fossil record, gets the residuals above and below the straight line, and then uses those residuals as a way of trying to model the reality. The difficulty with that, I think, and with sampling standardization, is that those methods cannot distinguish between a time of very poor sampling versus a time of very low diversity. In both cases, they won't distinguish between the two. So I'll hop past that. Forgive me just missing a couple there. This is important, and this is where the question is open. The contrast is between now, this is more or less a new version of the Raup 1972 figure. Here is the empirical data, here is the so-called corrected data from Alroy. And yes, we know that, of course, the raw data is subject to various kinds of error. I've certainly questioned whether this regime of correction is the correct regime of correction. It's a way of correcting the data, but whether it is actually doing what is claimed, I'm not at all so sure. Each time it is done, we get a different result. So the accumulation of data is changing the nature of the corrected output. And indeed also the Alroy method is generating some unexpected peaks in diversity. And I'm not sure I truly believe that late Cretaceous marine diversity was higher than modern marine biodiversity. But there we are. Some of the questions, and I think I'll come to some key questions in a moment, but some of those questions may be resolved by close study of the last 100 million years. That's the time where we have most knowledge. It may be difficult to resolve this debate that Raup set up in 1972 based on the Paleozoic. It may be more possible with the last 100 million years. And I just draw your attention to this kind of study by biologists. This is a very nice study by Alfaro, where he looked at the biodiversity of modern vertebrates. And based upon a phylogeny of fishes and tetrapods, he asked the question, which are the most biodiverse clades and when did they originate? And so he was able to use comparative phylogenetic methods to identify a number of clades shown by the yellow where the rate of evolution was very fast. The blue, I think, shows rates of evolution that were very slow. But if we concentrate on these yellow points, these are different groups of teleosts and certain mammal groups and certain bird groups. The interesting thing is they all fall in the Cretaceous. So he wasn't interested in the fossil record here. This is just based upon living forms. But nonetheless, bursts of evolution among mammals and birds and teleosts all seem to happen in the Cretaceous. And that relates to predictions that people had made from the fossil record, that there were the marine revolution and Cretaceous terrestrial revolution, things like that. There are very many questions we can ask in macroevolution. I won't read through these. These are open, large-scale questions that people might like to be able to answer. What are the drivers of evolution? Why are some clades more successful than others? How are they? Is that success due to adaptations, or are some of them triggered by mass extinctions? What is the role of mass extinctions in triggering later evolution? And all kinds of other questions like that, which Simpson was interested in and other people were, but until now it's not really been possible to answer these questions in a very adequate way. And hanging over all of this, unfortunately, are all those debates about the quality of the fossil record. I just wish we could put them aside and say the fossil record is great, let's forget all that stuff. But we can't. We absolutely have to keep thinking about that. But what I want to do in the last 2 or 3 minutes is just to finally point to a number of practical reasons why now is a good time for this kind of work, because many of these points or many of these methods and ideas were not available. And so we might have dreamt about this kind of thing a few years ago, but I think now we have the tools. So of course we have trees. And the list of 4 I'm just going to touch on briefly. So we have the trees, and I think they're getting bigger and they're getting better. And the fact that we now have phylogenies of all birds and all mammals, and we've done one for all dinosaurs, and those sort of scales of trees with hundreds of species allow you to do all kinds of calculations that maybe weren't possible before. A second point that I always try to stress to biologists, any geologists here will be very familiar with this, but biologists often forget that in the last 20 years the quality of geological timescales has improved enormously. So when I started in the business, people were very vague about dates. For example, people would quite clearly say the end Permian mass extinction maybe took 10 million years or 20 million years. We just don't know. Now the dating is much more precise. So, and magnetostratigraphy and cyclostratigraphy, all these methods allow paleontologists to talk about timescales and correlations from place to place with much more confidence than was possible before. Combining trees and time, there is a whole area of discussion which is important and quite helpful, I think, in trying to work out how best to put dates onto molecular trees. This is not a trivial thing, and this is an issue that concerns molecular biologists, phylogenomics people, and for them to understand the way the rock and fossil records work, and for us to understand how the Bayesian tree-making methods work and things like that is quite important. But again, this debate is happening now, and so we're in a better position than we were a few years ago in this question.